Alright guys, so 3.2 differentiability. So these notes are pretty quick, I guess, but they're very specific and you have to really understand why they're called what they are. You can see it very easily, but you have to understand this stuff, okay? So that's going to be the hardest part. So your homework tonight, the one that we do together, make sure that they all kind of look like that. Okay, so differentiability talks about, is something differentiable? So differentiable literally means that you can find a derivative. What is a derivative? A derivative is a slope. So if it's differentiable, then you can find a slope. There is a slope there, okay? So two things have to be true for you to be differentiable along some sort of interval. It's smooth and continuous. So the whole function, let's say you're talking about the whole function, is it differentiable? Number one, it has to be smooth and continuous. Well, if it's not continuous, it's not going to have a slope, right? So if you have a hole, that point doesn't have a slope, so it has to be continuous. And it has to be smooth. Like slopes follow these smooth curves. And then the derivative, which is the slope, exists at every point. So if you're smooth and continuous, basically if you're continuous and you can get a slope everywhere, then the function is differentiable. So let me show you 4 types of non-differentiability. Okay, there's 4. One is a corner. Obviously this looks like a corner. So for example, if you have an absolute value function, which looks like that, or if you have like a piecewise function, there's a lot of different examples you can use, but these are just, some examples, okay? So obviously this looks like a corner. So what makes it a corner, literally, is when the slope on the left side does not equal the slope on the right side. So we take this point, it is continuous along this point, but the derivative does not exist because it's not smooth, basically. So it's a corner, and the slope here and the slope here doesn't go smoothly. It doesn't smoothly transition, so that's why. So the slope on the left side looks like it's a -1. The slope on the right side is a +1, and that's a sudden jump of slopes, like it's very different, so it's a corner, okay? The other one looks almost the same, but it's not. Look, this is called a cusp. So a cusp is basically, and sometimes you can have like one piece that's a corner and one piece that kind of like curves, and that would be like a corner cusp or whatever, okay? But a cusp is basically when you have a left slope that's either positive or negative infinity, and then the right slope is the other one. So if you look at the left slope here, the left slope, this looks like almost a 0 slope up here, right? Almost a 0 slope, and then it gets more and more negative, more and more and more negative. So this is very, very negative slope right here. If I were to draw a tangent line, it would look something like this. So this is a negative infinity slope on the left side. And then all of a sudden on the right side, this is very, very positive, very, very positive, and then a little bit positive, and then barely positive, and then it looks like it's going to be a 0 slope over on the right side pretty soon, okay? So from negative infinity to positive infinity on the other side, or vice versa, it doesn't matter which side, it can look like this, and it's still a cusp, right? So that's what a cusp is. So functions that'll give you this would be like, so if you were to graph x to the 2/3 on your calculator, you'd see something like that. Also like piecewise functions. So if you have a parabola on this side and then you have a parabola on this side, then you might see some sort of a cusp. Okay, so some sort of a cusp situation. Okay, so a corner, a cusp, you have to understand what makes a cusp and what makes a corner, right? We're looking at those slopes. Okay. The next one is called a vertical tangent. So it is possible sometimes to have a tangent line with a 0 slope, like the very top of a hill. Like if this was a hill, we would have a 0 slope at the top. But then it's also possible to have a vertical tangent. So a vertical tangent looks something like we go from positive, like this is almost a zero slope, and then it becomes more and more positive, and this is like a almost positive infinity. It's so positive. And then on the right side, this is like super positive again, and then it turns closer and closer to zero. So positive slope, and then in between, this is like basically positive infinity. So positive infinity isn't a number, so this slope is like undefined, right? A vertical tangent would be like an undefined tangent slope. So then it says the left or right, both are positive infinity, like this one, or the left and right, both of those slopes are going to be negative infinity. So this is an example of negative infinity where you have almost a zero slope and then it gets more and more negative and it's super negative, and then it's again super negative and then barely a little bit negative, maybe like a -1 slope, and then almost a zero slope again. So negative infinity versus positive infinity. Okay? Do you have to know this? Not really, but if you have something, if you were to graph x to the 1/3 power, or basically a cube root of x or a 5th root of x, you would get something that looks like that. Okay, so you don't have to memorize this as an example, but when you find this on both sides, or you find this on both sides, your left slope and your right slope at a point, that's when you have a vertical tangent. Okay, be careful because x cubed is not a zero slope. X cubed, if I were going to use this terrible piece of paper, x cubed looks something like this, right? So that's x cubed. So x cubed actually right here has a positive slope, right here has a positive slope, but then over here it gets closer and closer to zero. So actually your tangent line right at the middle would be a zero slope. So it wouldn't be a vertical slope. So not x cubed, okay? Okay, the last kind is when you take, when you have like a jump. So obviously you can't be differentiable if there's no point there, right? So for example, like a piecewise function, or I would say like a step function, right? Which is like a round down function, which is the greatest integer function. So that would give you jumps as well, right? So a jump, it looks like the slope is 0 and then the slope is 0 on the right side. But if the limits are not the same, like if the y values, if the y values are not the same, then obviously, you know, it's going to be a jump. So we can't have a slope right in the middle because it's not the same point, okay? Does continuity guarantee differentiability? No. For example, you can have a corner of or a cusp. This is continuous, but it's not differentiable. Does differentiability guarantee continuity? Yes. You have to be continuous in order to be differentiable. That's part of the definition of differentiable. You have to be smooth and continuous. So yes, absolutely. Okay, on the back, I'm asking you, so basically, like, is it differentiable? You ask yourself these questions, okay? And then for your homework today, I'm asking you 1, 2, 3, 4, 5, 6. I'm going to do number 1 with you. You're going to answer A and B and C. Okay, and you're going to be very specific about it, and this is the kind of question that I'm going to ask you on the next quiz. Guaranteed, all right? So it's just 6 questions, but it will take at least a full sheet of paper, probably the front and back, okay? And I'll do number 1 with you, all right? Okay, so give it a try. All the answers, by the way, are on the right side. So you have to show all your work, and I'll post my work, but here are all the answers, okay? So good luck.